This is the first in a series of recordings that I'm doing to display memory on the Pico using Python. I'm calling that a just for fun set of videos because it's things that I do when I'm learning something new. The video is going to be kind of long, so I'm going to let you read these comments by stopping the video. All I'm going to do is highlight a couple of things here. I'm going to look at a description of one GPIO pad control register and print it raw, which means unformatted. I've given some references and indicated page numbers that might help you if you go back and read them yourself. I had to come up with these. Before we look at the code, we're going to look at a short presentation. Here's how memory is laid out on the Pico, starting at address 0 up through address EZ0000000. We'll be looking at two areas in this series of videos: the APB peripherals, which start at 40000000, and the AHB light peripherals, which start at 50000000. The APB peripherals, the areas we'll be looking at are the IO user bank, which starts at 4001 4000, and the pad control user bank, which starts at 4001 Charlie 000. In this video, we'll only be looking at this one, but we will mention the IO one. The labels here, in particular the pads bank 0 base, is a C-like label that we'll use instead of the hard-coded address. The AHB light peripherals we'll look at in a future video are for the PIO state machines. There are two blocks, one for each of the processors that manage the state machines. Now, we're not going to look at it, but just for completeness, here's what's in the IO user bank that we will eventually look at. The GPIO registers have two registers here associated with them, a status and a control register, one for each of the 30 GPIO pins. Within the RP 2040 datasheet, here's how they're described: the status and the control. In the pad control, which we will focus on today, are the GPIO pad control registers. The pad control starts at 4001 Charlie 000. The first word we're not going to look at. The GPIO registers start at offset 4 here and go up for 30 words. We'll take a quick look here in the data sheet. Here's the pad control as described in the data sheet. Note the label, note the address, and note that GPIO 14 is at offset 3 Charlie. Here is how one of those GPIO pad control registers are laid out. Everything is in bits, so when we do displays, we're going to use the bit format. We'll come back to this when we do the program. Now we need to figure out how to do the program. We're going to need MicroPython specific libraries. You have to go to this website and then drill down into libraries and then specific libraries. We're interested in machine. We've already used that for pen. We're now going to use it for memory access. And another library, UC types. I have that open here. Here's the MicroPython documentation page. We go down to MicroPython libraries. MicroPython specific libraries. Here we see machine and UC types. Go down to machine. Scroll down, and memory access is the first group shown. There are three, mem8, 16, and 32. To read or write 8 bits, respectively, 16 bits, respectively, 32 bits of memory. We're looking at words on the pico, so we're going to focus on the mem32. Here's some sample usage of mem32. You fetch a word by specifying an address and then print it using a format. Here's a format for hexadecimal, format for binary, a format for decimal. These work fine. These formats would work fine for Java and C, but have a problem doing hexadecimal and binary in Python when the x value is a negative integer. We'll see that later and how to fix it. Now let's go look at the code. Scroll down. We have a couple of constants that are going to help us when we do our displays. This was the address of the pad control block, if you recall from an earlier slide. This was the offset to the first of the GPIO pad control registers. Here are two functions. One is a specific function you should write once and then throw away, but we're going to look at it. And then the general function is the one you should end up using. So let's roll down just a little bit more and look at the code. Here's where the code starts. I'm going to go ahead and run it, and then we'll come back and look at what the show functions did. Here's where machine mem32 started was printed. Here is the raw output, and here is the general output. So let's first of all look at the raw output. You call it with a message or not. If you have a message, it'll print a message. But the main thing to look at is the print statement. And notice the hard-coded value for the memory address, 4001 Charlie 0 3 Charlie, which is really this. The pad block started at Charlie 000. The offset for GPIO 14 was 3 Charlie. Here's the value. The second show is the general one, which is the one we'll use in the future. You specify the pin number, and you have a message as well. Works a little differently. Takes 2 instructions. You use that hard-coded, you use that equated value for the base, plus the equated value for the offset to the first GPIO pad control register, plus 4 times the GPIO pin number. And you'll notice in the print statement, we have to put the GPIO pin number and then the 32 bits for the pad control register. And you'll see down here the values are the same here and here. Let me pull up the sheet again, scroll back to where we looked at the layout, and notice what we have here. I'm going to highlight right here. Now we can see, let me move it over. We can see that bit 0 is 0, the slew rate, whatever the heck that is. The Schmidt trigger is 1, as documented there. And the PDE, pull down enable bit, is 1. This is what the user pointed out in the comment to Paul's lesson 90 set of comments. So this is very interesting. The pull down enable is on automatically for all GPIO pins. Now we're going to look at the problem. Remember in earlier slide about Python and displaying integers. We're going to display a different number which comes from a different location in memory. We're going to see that it looks different in 2 cases. And we're going to produce the set of 2 cases by first of all displaying it now before any PIO program is run. We're going to run a PIO program and then display that same number again. That's down here. Let's scroll down. So before the PIO program ran, I'm having a hard time on it. Here are the values that are displayed. And you'll notice both the lowercase and the uppercase version, which are shown here and here, are the same. But in the after case, they're different. Let's take a look at how that after case is resolved. It looks good in the uppercase, but bad in the lowercase. So the second way we displayed was like this. Let me explain it. Python only knows sign numbers when it's displaying. And what we see at the bottom is that after the PIO program ran, the value in that word was negative. And it got displayed negative. Look down here. It's a negative number. And it's shown negative both in hex and in binary. That's not what we want. We want unsigned hex to be displayed when we print. So here's how that's taken care of. We take the word that we want, which is extracted into the variable x. We shift x right 16 bits to isolate the high order half, and then AND out what's in the upper half of that shifted word, and save that in variable s. And then in variable t, we take the value that came back and isolate the low half. And then we use this kind of print statement to print the upper half and the lower half in hex, the upper half and the lower half in binary, and everything looks fine down here. So, that's it for this video. Next video we'll move on to formatted values. Thanks for watching.